Before we introduce new knowledge, let's have a brief review what we learned in the last class. So we explained the electrons around the nucleus. It's not like the orbits of our planet, for example, Earth, surround the Sun. So we have to use, in other words, we cannot simultaneously determine the speed and the position of electrons accurately according to Heisenberg uncertainty principle. So then we have to use another term called probability, which means we can, how often, how frequently we can find an electron at a certain position around the nucleus. So basically, electrons, it's like the cloud, we call the electron cloud around the nucleus. So in order to describe the behavior of the electron and the orbital, so we use a few quantum numbers. So the first quantum numbers we introduced is the principal quantum number n. So what we should know is n could have these values, integers from 1 to 3, 4, for example. It's related to the size of and energy of the orbital. And we also should know when n increases and it's less stable and higher energy, bigger size. So the collection of the orbital with the same n we call it a shell. So the second quantum number we introduced is called angular momentum. We use L. So the L can have the value from 0, 1, 2, 3, and up to -1. So we also learned when the L have different value, for example, from 0 to 1 and 2, then the orbital name is given as S, P, and D. And for different orbital, like S orbital, they have different shape. For example, S orbital has a sphere-like shape, and P orbital has a dumbbell shape, and D orbital have the like a butterfly. But also we should know, and for P orbital, we have 3 different P orbital. For D, we have 5 kind of D orbital. They have different shape. For example, one has something like the dumbbell plus a donut, remember. So this slide introduces the third type of the quantum number. It's called a magnetic quantum number. We use ML, subscript L. So this quantum number is related to the orientation of orbital in space. So a loved value for this magnetic quantum number is from negative L, angular momentum quantum number, to the positive L. For example, when the n principal quantum number is equals to 1, since L only can be from 0 to n-1, so that means L only can be 0. n-1, 1 minus 1 is 0. So it's only possible. And in this case, ML also only can be 0 because ML is restricted, is limited by this value, cannot be larger than L. So if L is 0, of course ML is also 0. And when n is equals to 2, so L can be 0, can be 1. If L is equals to 1, then ML can be from minor L to positive L, that means from minor 1 to positive 1 also can be 0, right? So similarly, if n is equal to 3, just in case L equals to 1, of course L can be equal to 1 or 2 or 0, but just in case L is equal to 2, then ML can be from minor L to positive L, that means from minor 2 up to positive 2. Excuse me. So from here, you may realize there's a general trend. So the total number of ML is equal to 2L plus 1. Let's test it. For example, here, the L is equal to 0. 2L plus 1 is equal to 1, right? This is why ML, you see, have only one possible value. And when L is equals to 1, 2L plus 1 is equals to 3. You see here, we do have 3 ML values. Similarly, like 12 plus 1, 1L is equals to 2. That means 5. We have 5 ML value. So here give you example. When the L equals to 1, if you remember the first slide I showed you, when the L equals to 1 is corresponding to the orbital P. The name of orbital will be P orbital. So for P orbital, use that calculation, 2L plus 1, so it's equals to 3. So we have 3 possible ML value from the last slide, right? And you also can see we do have 3 p orbital here. We learned from the last class. It's named like 2px along this axis, 2py along this y-axis, and 2pz. So that 3 tell us there are 3 different kind of p orbitals. So similarly, when the d L equals 2, we have the d orbital. So the 12 plus 1 is equal to 5. This explains why we have 5 kind of a d orbital. Yeah, that is just because L is equal to 2 and the possible is 5 kind of d orbital. So we learn all the orbitals in this given principal quantum number we call the shell. And for example, that's 4 orbitals. They are all have the same principal quantum number. We use this number, yellow. And so they all belong to the same shell. So now let's take a look at another term called a subshell. The subshell means all orbitals with the same number like this, as well as the same letter. So that because that number tells us the principal quantum number n, so that letter tells us the angular momentum quantum number. For example, when the L is equal to 0, it's named S. When it equals to 1, it's named as P. When it's equal to 2, it's named D orbital. Anyway, so these 3 have both the same number and the same letter, so they are called subshell. They are within the same subshell, yes. And these belong to the 4s subshell. So similarly, these all belong to the 4d subshell. These 5 different orbitals. So this slide we introduce a very important concept. So this in order to describe the electrons in an orbital, we use something called electron configuration. Some textbooks also use spectroscopic notation, use that name. So basically, there are three parts in our electron configuration of this notation. So the first one is the number in front of letter. I think we already talked about that. That indicates the principal quantum number n. For example, can be 2 or 3 or 4. That indicates the principal quantum number n is equals to 2 or 3 or 4. So this letter tell us the type of orbital. For example, it's P or D or F or S orbital. So that is determined by the angular momentum quantum number. Like we said, when this L have different values from 0 to 1 to 3, and their name is named as like S, P, D, F. So this superscript number here indicate the number of electrons in that orbital. For example, if this is 1, that means there's 1 electron on this orbital. If it's 2, that means 2. For p orbital, if this one is 3 or 4, that means 3 or 4 electrons on that orbital. But for s orbital, maximum can hold 2 electrons. We will talk about that later. So here, we introduce the last quantum number. We call the electron spin quantum number. We use ms. The subscript letter S means the spin. So there's one very important principle in this chapter. Is called a Pauli exclusion principle from a German scientist, Pauli. So that principle says the 2 electrons occupying the same orbital must have opposite spin.
Which creates a magnetic field. Spinning electrons produce magnetic fields with an identifiable magnetic polar orientation, so-called north or south. The polar orientation of a given electron is determined by the direction of its spin.
Yeah. According to that principle, either you have this, either you have this kind of spin or you have that kind of spin. Yeah. Is N up, S down, S up, and down. So that means ms have only 2 possible values. One's positive half, one's negative half. And so, okay, I will show you this video too. Yeah. So this, you see, we have many electrons, like 7 electrons. Yeah, either they spin that way, we give the electron spin quantum number positive half, or they spin the opposite way. We give the minus half. Yeah, it's only 2 possibilities. This is why the ms only could have 2 possible values, easy to memorize compared with another 3 quantum numbers. Okay, let's do some eye clicker. I will, let's see. So which quantum number determines the size of orbital? If you still remember the previous slide we talked about, the answer is A. The principal quantum number n determines the size and energy of the orbital. So this type of the question will be like the question you will be tested in the quiz and exam. So from the last class and today's class, so we know that each electron can be described by its unique set of 4 quantum numbers. So the first 3 quantum numbers, like a principal and angular momentum and magnetic quantum number, they tell us where the electron lives, where you can find electrons. In other words, from which orbital you can find the electron. For example, if you have this set of quantum numbers that tell you, okay, the principal quantum is equals to 2, then write down 2 here, and the L is equals to 1, that's corresponding to p orbital. To remember, 1L is equals to 0, 1, 2, 3. The orbital name is named like SPDF. Okay, 1 is corresponding to p orbital. And this one can tell you either it's px, py, and or pz. So, okay, in short, that 3 orbital determine where you can find electrons. The last quantum number tell us either that electron is spin that way or another way, positive and negative. Similarly, the same principle, if we have this set of quantum number, we can say this orbital, the notation can be written like this. This 3 is here, and 0 corresponds to the s orbital, and so similarly like here. If we have this set of the quantum number, and that will be the 4d orbital. And so the orbital will be the one of the 5 orbitals, and we have certain spin quantum number. So let's do more in-class practice. For example, let's see which set of quantum number is wrong in this case. For example, what is the problem for this set of quantum number? So the answer is, here we learn the principal quantum number n only can be from 1 to 2, 3 integers, but not including 0. So the principal quantum number cannot be 0. So this is a problem. N cannot equal to 0. And let's take a look at here. What is the problem here? So I can say the L value, possible value, if you still remember, only cannot be bigger than n. It only can be from 0 up to n minus 1. But this one is larger than this one, so it's wrong. Only can up to n minus 1. Let's take a look at this one. How about this one? Seems here is okay, but this one, the ML, can be from minor L to positive L, but not beyond L. So this one is larger than this one. So this is a problem. And so the last one, here is okay, but the spin quantum number only can have 2 possible values, either positive or negative half, cannot be 0. Okay, so this is in-class practice. So this slide summarizes what we learned from these 2 classes. I don't want to repeat the same knowledge, but it's good for you. I posted this one on Canvas so you can review this knowledge. For example, each orbital in the atom has a unique set of 3 quantum number, the 3, and can hold up to 2 electrons opposite spin, and the principal quantum number n, for example, relative size and angular moment quantum number can have this value, for example, And when the principal quantum number increases, you see size increase, and so on. So the angular momentum quantum number related to the shape. When they have the 0, 1, 2, you have different shape. And the last quantum number tell us the spin of that electron, either spin up and down. Okay. So this is also very important slide. Very good summary. So each orbital in an atom has a unique set of 3 quantum number we learned, and can hold 2 electrons for one orbital because the Pauli exclusion principle. Yeah, you only can hold 2 electrons. If there are third electrons, that means they will have the same spin quantum number. Yeah. And so let's take a look at when the n principal quantum number equals to 1, then L only can be equals to 1, right? Because L can be from 0 to n minus 1. So n minus 1 is equals to 0. So 0 corresponding to the s orbital. So this is unique, only possibility. And if s is equal to L is equal to 0, the ML also can only be 0, because ML is equals to possible values from minus L to positive L. Okay, this one equals to 0. So this is one set of the quantum number, mean one orbital. So this one orbital can hold only 2 electrons. These 2 electrons, because one electron has a spin quantum number of positive half, the another one has a negative half. Yeah, only 2 possibilities. It means 2 electrons. And so let's see when the principal quantum number n equals to 2, then the L can be 0. L also can be equals to 1, right? Because 1, 2 minus 1 is equal to 1. Yeah. So when the L is equals to 1, so it's called p orbital. So we learned there are 3 p orbitals like px, py, pz, like this. So when the L equals to 1, the ML is equals to 2L plus 1 is 3. This also tells us, okay, we have 3 magnetic quantum number. So if we add this together, we have the white. Let's look at the white. We have 3 kind of this quantum number. That means 3 orbital. So these 3 orbital, each one can hold 2 electrons. So maximum this white orbital can hold 6 electrons. 3 times 2 equals to 6. And so if principal quantum number n is equals to 3, the L can be 0, again corresponding to S, 1 corresponding to P, and 2 corresponding to D orbital. So let's please look at the color here. This one corresponds to here, and this 3 is corresponding to the P orbital, like here. We talked about that already. For D, if the L is equal to 2, 2L plus 1 is equal to 5. We have 5 different orbitals. So 5 different orbitals can hold 10 electrons, because each orbital can hold 2 electrons. Yeah. Up to here, let's similarly. So if the principal quantum number equals to 4, and these are same as above, but we have one more possibility when n equals to 3 is F orbital. For S, we have 7 possible orbitals. 7 orbitals hold 14 electrons. And so altogether, this whole orbital can hold 80 electrons. This can hold 18 electrons. So this is why we summarize the possible electrons in that shell is equal to 2n squared. Yeah, we can check that. For example, when n equals to 1, 2n squared, n squared is equals to 1, 2n squared equals to 2, right? When n equals to 2, so n squared equals to 4. 4 times 2 is 8. Exactly, we have 8. And here, when n equals to 3, 3 squared is equals to 9. 9 times 2, 18. Right? Perfect. Yeah. So this is summary. This is another brief summary for your, just for your memorizing. Yeah, it easily. It tells us when the angular momentum quantum number L equals to 0, 1, 2, 3. I hope you can memorize their name, and subshell is SPDF. Yeah. And the number of orbitals will be S have 1 orbital, and P will have 3. You may remember PX, PY, PZ, and D have 5 orbitals. 5 different orbitals. We showed you in the last class how to draw it, And the maximum number of electrons can hold is this one. So each one times by 2, you will get this value, because each orbital can hold 2 electrons. Okay, here again I show you how to use learning objective I posted on Canvas to study for this class. Yeah, the highlight here says, okay, in the last class we talked about a Bohr's model and the Heisenberg and Thornton principle and atomic orbital. And here we talk about the 3 quantum numbers to be used to define an orbital of atoms, and list the allowed values for each quantum number, and assign orbital name to allow a set of quantum number. Also sketch the shape of the following orbitals on piece of paper. I will post the sum in class practice on the Canvas. Also, we introduced the electron configurations, which means how the electrons are distributed among the orbitals like this. For example, this is principal quantum number, the orbitals, and how many electrons are on that orbital. So, yeah, it's good to know. For the atom in its ground state, we talk about that ground state, excited state, electrons only occupy the orbital of the lowest energy. So that is understandable, like the water, tend to flow down because they want to have the smaller potential energy. If same things, if I drop something, they will go down to the ground. Electrons the same, they like to stay in the ground state. So we talk about that. Okay, we don't want to repeat that one. I'll just let you know there's another way to describe the electrons. So we call the orbital diagram. So the diagram showing how the orbitals of the subshell are occupied by electrons. Compared with the previous one, we only can have this kind of information. But here, if you use this diagram, they can tell you, okay, there are 2 electrons located in this 1s orbital. Also, they have the different spin. You see different spin quantum number, like spin up and spin down. So you cannot put another electron here, because if you put another one, either you spin up, it will be same with this one, or you spin down, it will be same with this one. According to the Pauli exclusion principle, there's no 2 identical electrons can be found in the same orbital. So they must be different. So this is why maximum this orbital hold 2 electrons. Same as here, s orbital can hold 2, but for p orbital, we have 3 kind of p orbital: px, py, pz. Yeah, maximum actually, this 2p orbital can hold 6 electrons. But here, if we only have 2 electrons, we simply just put 2 electrons there. So altogether here, you see we have 6 electrons. If you look at your periodic table, you know this is carbon, right? Carbon have 6 electrons. So, okay, the example is like this. So the lithium, use this diagram that we can describe the lithium, for example. This is a notation we learned, and this is a diagram. And similarly, if for neon we have 10 electrons, we can write down it like this: 1s2, 2s2, 2p6 electrons. And if you ask why it should be like that, can I put 3 here? Yeah, for example, then I think this diagram can tell you better, because you only can put 2 electrons with opposite spin like this. There's no chance to put another one. Yeah, according to the Pauli exclusion principle. This is why we have 1s2, 2s2, 2p6 configurations. So, okay, so here is a Pauli exclusion principle we talked already. So not all arrangement of, he found not all arrangement of electrons among the orbitals are physically possible. According to he summarized the experimental observation, he stated that no 2 electrons in the same atom can have the same 4 quantum number. If the first 3 quantum number are same, so the last quantum number, like spin quantum number, must be different, cannot be same. If the 4 quantum number are the same, it's prohibited. Yeah, it's not possible according to this principle. So from here, we introduce how to fill the electrons into the orbital. So this is called Aufbau method. It's a German word. English is called building up method. For example, like here, this is kind of building up of the electrons. But here we want to know what is the principle, why. So first, each orbital can hold only 2 electrons of the opposite spin, like the Pauli exclusion principle said. Yeah, for example, here we start from here, hold up to 2 electrons. We have to fill the electron on the higher energy of the orbital. We know 2s have the higher energy compared with 1s. Why? Because we talk about that the principal quantum number determines it's related to the size and energy. So here we have the higher principal quantum number, which means higher energy. So, okay, let's see. The second statement said in a set of orbital of the equal energy, for example, if we have these 2ps, 2py, and 2pz orbitals, so there are 2 ways to fill. After I fill this electron, if I have 1 electron, I have 2 ways. Either I fill this electron here, or I can fill the electron here first, before I put the electron here. So which way is preferred is correct. So here it says each orbital get 1 electron first, before any orbital get a second electron. This is called a Hund rule. So the according to the Hund rule, the desirable for the most stable configuration is each orbital get one electron first before you feed in the second electron here. You can understand this that way. For example, if we have, 12 chocolate, but we have 10 people, for example, we will say, okay, first everybody get one chocolate first before you can get no one can get the second chocolate before each one get one. Yeah. So this just help you to understand it. Yeah. According to that principle, the electrons for boron, for example, if we have 5 electrons, will be filled out. This way, first we put 2 electrons on this orbital, and after this is filled, it's full, we cannot put more. We put another 2 electrons on the upper level energy orbital, like 2s. S only can hold 2 electrons, and we have 1 electron left. We will put in onto the p orbital, like this boron. And I will show you the video. The video showed you how to fill the electrons for boron and continue like a carbon, like oxygen and until neon. Yeah, please watch this video. You see, the sequence will be like that, according to the Hund rule. Each one get one first, and then if we have more electrons, we fill in. Also, this corresponding to the different elements. Let's play it again. Boron, carbon, nitrogen, oxygen, fluorine, neon. Yeah, so this is a way to build up electrons onto the orbital. The third statement said the electrons are added to the unfilled orbital of the lowest energy first. I think we already used that principle already. Yeah, do you remember when we filled in the electron here, we start from here, right? Lowest energy. We cannot fill this one first and then do here, no. Like I said, this like to stay in the lower energy first. So according to the third statement, so the order of the filling the electron into the orbital will follow this sequence. Because the 1s have the lowest energy, here shows you the energy order. This 1s have lower energy, but 2s, the principal quantum number increase, the energy increase. But you may ask why these two have the same principal quantum number, they have different energy. That is a very good question. For single electron atoms, for example, here, they have the same energy. Yes, however, if one atom have multiple electrons, the electrons after layer of electrons will be screened, by the inner electrons. So that causes the energy shift.
In a single electron atom, hydrogen, subshell energies depend only on the subshell's principal quantum numbers. In a mini-electron atom, the presence of electrons in one subshell affects the energy of other subshells. Consequently, the subshells are not filled simply on the basis of the principal quantum number.
Yeah, very good. So, based on that, I think what you should know is this sequence. Yeah, the energy sequence, like 1s, 2s, 2p, 3s, 3p, 4s, 3d, and 4p, 5s. So that is exactly this. So how to memorize, the lots of orbitals? How can I know if the 3s or 4p, which one has the higher energy? So my the tip I can give to you is, at the beginning it's easy. For example, we start from 1, right? The principal quantum 1 is the lowest. And then principal quantum number increase to 2. It's also understandable. And increase to 3. That is all follow the normal sequence. Up to 3, only from here, there's something abnormal come up. Suppose 3D have the lower energy than 4s because this principal quantum number is smaller than 4. 3 is smaller than 4. However, like the video I showed you, due to the screening effect of the different electrons, the final conclusion is the 4s have the lower energy than 3D. We have to accept that fact. This is why I write down 4s here. So I memorize that this way. So up to here is okay, and then I can see 3, 4, 5, 4, 5, 6, 4, 5, 6, 7, right? Just like counting the number 3, 4, 5, 4, 5, 6, 4, 5, 6, 7. I use this table. I can memorize that one. I mean, even 20 years after my high school, I still did not forget about that. I use different color. But if you still feel that is difficult to memorize, here's another tip. You may write down like 1s, 2s, 2p, 3s, 2p, 3d, 4s, 4p, 4d, 4f, like that, and then you use this arrow. So then you follow the sequence of arrow. You see, I start from here, I do here, I do here. I continue this one, so this one energy, and higher than this one, you see, and then after 4s, I go 3d, 4p, 5s, 4d, 5p, 6s, right? Just follow that sequence, you will end up with exactly the same sequence as here. And then you simply fill in the electron, maximum electrons each orbital can hold. For example, this can hold 2 electrons, 2 electrons, p can hold 6 electrons, and 2 electrons, 6 electrons, and 2 electrons, and 6, sorry, can hold d electron, because d have 5d orbitals, to remember. 5d orbital can hold 10 electrons, and p again can hold 6 electrons. So you can write down the superscript number on each orbital. Depends on how many electrons we have. Yeah. For example, for carbon have 6 electrons, you can write down 1s2, 2s2, 2p2 is done. It's finished because carbon only have 6 electrons. I think another way to, for your convenience, another way is to make this drawing. This one will be same as the last one. Here, it's the same, just the habits. Here we put the lower energy at the bottom, and the last one we put the lower energy on the top. Yeah. So for here, you also can draw something like this. Yeah, I just give you alternate option. Okay, I think we stop here for this class. And let me see. Stop